about big data, and then the technology related to big data. And then also you learn from George about pre-processing or like statistical descriptive analysis, including visualization. In this case, I think you already learned how to pre-process and then to visualize your data. For our material today, I would like to use R and also Python, but now I think it's better to use R first because Python you already have learned. Wait a minute, why I couldn't admit her? Okay, here. First, I ask you to install the R software, which is open source software. In here, you can see on the screen that if your laptop is Mac, and then you have to download R for Mac operating system. And then if you are using in Linux, so you have to click this one. And then if you are working in Windows, so you have to click this one. Could you see that? Has anyone installed this R or who's not yet?
Already, ma'am. Already installed.
Abdul Majid, I will open my presentation. So this presentation, actually, I prepared it for 20th of October, but now I think we use it for today. So my topic is about correlation and regression, okay? So what is correlation and what is regression? We should learn from the definition. So correlation is a degree of relationship or association between two variables. For example, the two variables, we can call it as x1 and also x2, okay? The correlation value, it will be between -1 and the maximum is 1, okay? Then there are two types of correlation. The first one is population correlation. The second one is sample correlation. If it is population correlation and then the symbol is like this, you can pronounce it as rho. And then sample correlation, the symbol is this one, which is R, okay? And then for our computation, mostly we will deal with sample correlation, okay? So how to compute the correlation, we will learn it later manually and also by using the R software, okay? I also will send you the link or books, which is about doing correlation and regression with Python. So we can discuss it later. Because this is about correlation and this is about two variable. For example, here we have two variable which is x and y. Okay. The first picture in here is we have four pictures. We can say this one is A, B, C, and D. I have to use actually something else, but I don't prepare it for today. Spotlight, but later maybe next week. Okay. We can see from the first one here between X and Y, we can see that there is association or relationship. If X is becoming bigger and then the Y also becoming higher, okay? And then for the second one, which is B in here, you can see that there is relationship or association, but it is not about linear relationship. But for B, on the top one, we can see that there is linear relationship. And then if there is no relationship or no association, you can see the picture from part A in here, which is on the bottom and on the top here. We can see that there is no association at all, at least linear association. And also for the top one, we cannot see the pattern. If it is like B, which is on the bottom here, on the left side, on the bottom, you can see that there is a relationship or association, but it is not a linear relation. Okay, the relationship is not linear. It looks like this is a quadratic relationship. Okay, so that's about correlation. And another illustration about correlation is something like this. We can see that if we have this one, this picture, which is there is a value 1, this means there is association or relationship, and the degree of its correlation is 1, which is positive. If it is like this, okay, the second one, this is something the illustration or visualization when your correlation value is about 0.8. Okay, and if it is 0.4 or 0, and then if it is minus 0.4 or minus 0.8 or minus 1, we have this one, which is the first condition of the first three picture. Okay, so this one is 10 to the right side, and this one, the last one, is 10 to the left side. That's why in here is the first one is +1, the correlation value, and then the last one is the -1 correlation value. Okay, and you can see as well some illustration when the correlation is 1, and also some illustration when the correlation is -1 and 0. Okay, and the last row here, there is a relationship, but it is not about linear relationship. We know that the correlation sometimes we can call it as like copula in statistics. So if it is copula and then there is a relationship between the two variable or two or more than two, but maybe the relationship is not linear at all. Okay, so we can see, for example, the second from the last, it is circle, something like this, or maybe this is ellipse. Okay, this means there is a correlation or relationship, but it is not linear. So today we only would like to learn about the linear relationship between two variables, which is we can call it as x or and y, or x1 and x2. If you would like to use, for example, y1 and y2 or z1 and z2, it is possible as well. Okay, so why I give you this illustration, I mean, if you have the data, before you are sure that there is correlation or you compute the relationship between these two variables, and you have to visualize this first. So you have the data from internet, for example, you are doing the pre-processing. Pre-processing is you have to discard or delete some unwanted data which is maybe not suitable enough for your further analysis. For example, there is an A, or maybe there are some error. Maybe it is just like globe, something like that. So that's why you have to do pre-processing. Once the pre-processing is finished, and then you can do visualization. If you have two variables, so we can do the visualization, the relationship between them by using a scatter plot in R, okay? And then after that, you can see if there is relationship or not between these two variables. If there are many variables, you still can compute the correlation, but it is one by one. For example, you have 5 variable, and then you can see the relationship between x1 and x2, x1 and x3, x1 and x4, and so on and so on. Okay, so and then based on that, if you would like to make produce a model, and then you can see which one actually you can include into your model by just look at the correlation value or using the visualization. Okay. The correlation can be parametric correlation or non-parametric correlation. I think actually you should already learn about type of data in statistics, okay? Because if you didn't learn about type of data, it is a little bit maybe something new. But if you already learn about statistical basic, and then you know that there are 4 types of scale measurement. For example, in here is interval, ratio, and then what else? I don't remember. Interval, ratio, and then what else? Nominal and ordinal. Okay, that's the 4 scale measurement. Okay, I remind you about the 4 measurement scale. Do you remember about this? The first one is nominal, and the second one is ordinal. The third one is interval, and the fourth one is ratio. You only need to know about this kind of data because you would like to analyze your data. Okay, so that's why you have to a little bit expose for this one. So nominal, for example, about gender. You can say, for example, gender is male and female. Okay. Your data sometimes assign a number to this kind of data. For example, male is 0. Let me use another one. For example, male is 0 and then female is 1. Or maybe male is 1 and then female is 0. Or maybe male is 1 and then female is 2. Something like that. Okay. So this is to quantify your data, which is from nominal becoming numeric. Okay. And then for ordinal, I think, for example, grading score for your exam, which is between 0 until 100, or maybe 0 until 10. Okay. In this ordinal, there is a ranking or the order. For example, 100 is greater than 99. But for the nominal, there is no order at all. If, for example, I use 0 for male and then female is 1, it doesn't mean that female greater than male. Okay, so this is just a sign number. But for ordinal, if, for example, I have grade 65, and then you have grade, for example, 80, so you are better than me. Okay. For the interval, I think one of the most popular one about this one is about temperature. For example, in Fahrenheit, or maybe in Kelvin. Okay. So if I say 0 degree in Fahrenheit, and then in here maybe Celsius, so it become, I think, minus 32, right? In Celsius. If I say 0 degree in Celsius, maybe in here is 32 degrees, something like that. Okay, yeah. In ratio, I think you can say, for example, about weight of someone or height of someone. So if I say this is 0 kilogram, so we have no weight at all. Okay, but if I say 0 in temperature, so it still have the temperature, and then the value is 0. So it is something like non-absolute value, but for the ratio, there is an absolute value about 0. Okay. If, for example, I have a height 0 centimeter, it means I don't really have height at all. Okay. So this is about the measurement scale, and then we can return back to our original presentation. Okay, let's continue. There are two kind of correlation. The first one is about parametrics correlation, and the second one is non-parametric. So it depends on the data. If the data is in nominal or maybe ordinal scale measurement, which is in ranking, so we can say it is for non-parametrics correlation. But if it is in interval or ratio, and we can say that it will be parametrics correlation. So one of the parametric correlation is, we call it as Pearson correlation. Okay. So what is this about? This Pearson correlation, for example, you have two x1 and x2. Each one has an observation. We can say the observation is, for example, n, okay, small n, because if it is capital N, then it is for population. Okay. The first formula in here, actually, you compute the sample correlation. And then the second one is for population correlation. So what is the difference between this one? If it is sample correlation, you can see that the symbol is small r. And then this one is standard deviation for the first variable, which is x1. And then this one is multiplied. Sx2 is mean the standard deviation of the second variable. And then this one is the covariance between x1 and x2. Have you learned about how to compute the covariance before?
Yeah, miss.
Okay then. Okay. And then for the population correlation, which is rho, the difference is between two of these in here. You can see that this one is sigma. Sigma x1 is mean the standard deviation of population, the first variable, and this one is the second variable. And for the third formula, there is one missing actually in here is +1. Okay, so the correlation value has to be between -1 until +1. So we can make it correction in here. Okay, so now is for the non-parametrics correlation. This parametric correlation is we can define as like this. Still, we have two variable. We can say the first and then the second. And this one formula for the sample correlation, and the second one is for population correlation. And this is the formula where di, actually the difference between the first observation from the first variable, the I observation of the first variable minus I observation of the second variable. Okay. So because we already compute this correlation, so we can do the hypothesis testing. And for the Sperman correlation, so it's mean we are using this one. Can you see? Maybe this is not clear enough. I think this is clear. But this is still in Bahasa Indonesia, but some of them maybe you can guess directly. So for this Sperman correlation, I think you need the Sperman table, which is we can find it from a statistical book or maybe from Google as well. And there are three kinds of hypotheses. If, for example, you would like to learn about this hypothesis testing, maybe I can prepare it not to delivery on the online lecture, but I think maybe I can just prepare the material about the hypothesis testing. Okay, if it is needed, please let me know. Okay, so this one is the hypothesis testing for Sperman correlation. So there are two kinds of hypotheses. The first one is a one-sided hypothesis, which is the second and the third row in here in this table. And then there are Another one is suicide of hypothesis setting, which is the first row in here. So the difference between these two kind is the how to say that this one is for hypothesis null, it has to be equal, and then for the hypothesis alternative or hypothesis one, it has to be unequal. And then for this one, this is one side hypothesis testing. This is the right side hypothesis testing, and then this one, the left side of hypothesis testing. So in terms of this hypothesis testing, there are two decisions. The first one is you reject hypothesis null, or you don't reject hypothesis null. Reject hypothesis null, if it is the first type of hypothesis testing, it means you are taking the alternative hypothesis testing, and so on and so on. Other will be similar. Okay. If it is not clear in here, then you can ask me later. Okay. And then now we learn about another type of non-parametrics correlation, which is about candle rank correlation. Okay. And this candle rank correlation, how to compute this one manually, it is like this. And then S is the candle rank correlation, you only have two variables, but for partial rank correlation or just partial correlation, so it means you have more than two. So maybe 3, 4, 5, and so on. Okay. And then regression. What is regression? So the correlation is a degree of relationship between these two variables. Okay. And then the regression is a functional relationship. In correlation, because it is degree of relationship, it means the final product is a value of correlation between two variables. And then this regression, because it is a functional relationship, the final product, it has to be a function. Okay, a function which is built based on independent on dependent variable. So in correlation, you don't have to divide between dependent and independent variable. But in regression, you have to identify which one is dependent and which one is independent variable. It is very important to identify which one is independent or dependent variable. Why? Because the dependent variable is the only variable that you would like to predict. Okay, so if you use dependent variable or you identify it wrong, for example, it has to be dependent variable, and then you say it is independent variable. So it means you are using this predictor. No, you are using this response as predictor. So it will be reversely the result. Okay. So that's why you have to identify first which one will be the independent, which one will be the dependent. Okay. So maybe you would like to ask me, how can I identify this independent or independent variable? It is easy. Actually, you have to look at the research question. If you would like to predict something that you would like to predict is dependent variable. Okay, just as easy as like that. Okay, and if you would like to know the contribution of the variable towards something, the contribution of this variable is mean this is the independent. For example, I have a question like this. For example, let me use this first. So for example, in here I have salary, and then I have age, and then I have education level, and then I have gender. Okay. So this one is this one, and this one, and this one. So for example, I use this just first I use everything equal, okay? So this is the first variable, and this one the second, and this is the third, and this is the fourth, okay? So I would like to know the contribution or the effect of age, education level, and gender towards salary, okay? So in this case, I would like to measure the effect of this one. Let me use different color. I would like to measure the effect or the contribution of age someone and education level of someone and the gender of someone toward this one, right? Okay. So it means this one you want to predict. You want to predict. Okay. And this one, three of them, you would like to measure the contribution or the effect. So this one is independent variable. Independent variable. Okay. This one. And another one in here is, maybe I should use different color. Let me. This one is independent variable. And this one is dependent variable. Okay, sometimes you can find in the statistical textbook, you say this is dv, v, yeah, and then is iv. Okay, something like that. Okay, but if you identify it wrong, for example, you would like to measure the contribution of salary, age, and education level towards gender. So do you think gender is defined by the salary, the age, and education level? Statistically, it is okay. Mathematically, it is okay. We can predict anyone for anything from here based on these four variables. But scientifically, gender could not be identified or could not be defined by education level, age, and salary. So this will be something wrong. So that's why the identification which one is independent or dependent variable, it is very, very important. You shouldn't identify or predict something which is against the nature or against the scientific thing. Otherwise, if you would like just to prove it, okay? Me, for example, I am now 48 years old, and my education level is doctoral, and my salary is, it is not the real one for the salary, but for age and education level is the real one. My salary, for example, just 500 US dollar. Because of this, and then my gender, now is my gender is female. But if you are doing this modeling, and then maybe you can predict that my gender is not female but male. It is something okay. Just modeling is okay, but your modeling has to be according to nature and also according to the scientific community. Okay, so that's why it is very important. Otherwise, it will be very ridiculous. Okay. I guess you remember about the Nobel Prize, and also there is a Nobel Prize. The Nobel Prize is a very, very prestigious one. And then the Nobel Prize, it is still prestigious. Why? It is scientifically proven. For example, I remember that one group of researchers in UK, they can guess someone how to say, someone profession by just looking at the measurement of their hip. This is for men, not for women, okay? If their hip is, for example, I don't know, maybe 34-inch or something like that, I don't remember, okay? If their hip is more than this length, and then they can say that the profession of this person is a taxi driver. And it has been scientifically proven. Most of the taxi driver in UK, they have the length of their hips. It is wider than the average of people in UK. Okay, so if now, for example, he already retired from being taxi driver, maybe they can ask that maybe one of them, usually in the previous one, they have a job as a taxi driver. Okay, so it is scientifically proven. It is something a joke, but it is to be addressed by scientific community, and it has been acknowledged as well. Okay, so let me continue after this. Because of in regression, we are dealing with independent and dependent variable. So you have to also to be notified about this kind of regression. If it is independent variable only once, and dependent variable is only one, and then you can have this simple linear regression or polynomial regression. If your independent variable is only one, and then your dependent variable is more than one, and then you can have a multivariate regression. Okay, so variate in here means dependent variable. It is something that you can try to memorize it. Multivariate is mean dependent variable. If I say multivariate, it means more than one. The dependent variable, it is more than one. And then if your independent variable is more than one, for example, 2, 3, 4, and so on, but your dependent variable is only one, and then you can produce multivariable or multiple linear regression. And then for the dependent more than one, you can have this multivariate multiple linear regression. So keep in mind that mostly we will have exercise. The dependent variable in here is only one. So it is only this green area. But if, for example, for your final project, you would like to use the yellow area, please let me know. Okay. So what is the linear model? The linear model, there are two kinds of linear model. The first one is linear in parameter. The second one is linear in variable. For this kind of model like this, it means this is the linear in parameter and also in variable. So what is linear? Maybe you remember when you learn about function for calculus 1. Linear function is mean the highest power of this function is 1. The highest function. Okay, the highest power of this function. So if I say it is non-linear, so it is possible maybe the highest power is 2, 3, 4, and so on. When I say power, it means the degree. The degree of this function is more than 1. So let me show you this one. In regression, for example, you have one independent variable, and then you have one dependent variable. Okay, so this is independent and this is dependent. In here, you can form, the first one is just simple linear regression, which is like this, a plus bx, something like this, okay? This one, a and b, it is only, the degree is only 1, or the power is only 1, and x as well. So that's why we call it as linear regression. And you also can form polynomial regression, which is, for example, like this: a0 plus a1 x power 1 plus a2 x power 2, and so on. Maybe the last one is am x power m. So this is the higher degree. So that's why we call it something like this is polynomial degree m. So that's the highest degree or the highest power. Okay. So if you only have this one and then dependent variable also one, this can be computed by applying the model. Okay. And then let me go back to here. Okay. In matrix, you can write down this model as like this. So why I introduce about the matrix to you, I mean, if you would like to have programming about how to compute the parameter of the coefficient of this model, and then you have to understand about the concept behind this one. So but the concept behind this one actually is about matrix and vector. When you already, I think you already learned about how to write down the vector and matrix in Python, and some of you also maybe have learned about how to representing the vector and matrix in R as well. Okay, so this one is like this, and then when you would like to compute this one, so this is the model that we would like to estimate. You have this data y, and you also have this data which is x. Okay, and then the only one you don't have is beta 0 and beta 1 and this residual or error. But we can compute error when you already have the estimate model. So this beta 0 and beta 1, we have to estimate. How to compute this one? You can see from here. So this one is only algebra. So for example, I have this one like this. You can say that this is y, this is x, this is beta, this is error. It has to be like this because it is a vector. This is the original model, but when you would like to estimate, you directly write it as like this. And then how to solve this problem? Do you remember this one? Y is equal to x multiplied to b, and y is a vector or matrix, and x is a metric. So how to compute this one? Beta is equal to, do you remember this? This one is equal to this one, right? Yeah. Do you remember this one or you don't remember this? So this one comes from okay, and then because of this one, so we try to find out because we would like to just left this one, right? So it has to be, this is the inverse from this matrix. Okay, so this one will become identity matrix. Do you remember that one? I guess you will remember that it become identity matrix. So that's why this become this one, and this one becoming this one, and this is the same. So that's why you got this result. No, you got this result which is equal to this. Okay, so it is only about matrix. You have to understand the concept behind of the computation in one software in Python or in, for example, R. Why? Because if you already understand the concept behind this one, so you can improve something. But if you only use the package based on, for example, R package or maybe the other package from Python, you only use it, but you don't have time or you don't know exactly how to improve this one if something gone wrong. Okay, so that's why if you already understand about the concept of matrix and also about the vector and also about the norm and everything in linear algebra, I think that's very good. Okay, let me continue. Okay, so this one is similar, but in here I give you insight, which is about the polynomial degree 2. This one is only one independent variable, which is x. And then this one is only one dependent variable. But in here, as I told you before, that we can form the polynomial regression. And this one is the degree of this polynomial is just 2. And how to solve the problem is similar to this one. And you can also use the package from R maybe and also from Python. Okay, and then in general, if it is linear regression, so actually this is like this one. So you can see that there is no highest degree than 1 for the power or the degree in here. So that's why we call it as linear regression. And this one is the representative of y in here, and this one is for x, and this is for beta, which is we would like to estimate based on y and x data. Okay. One, you have estimate the model, so you can do further. What you should do, the first one is you have to check the normalization, which is about the error of your model. So how come I can compute the error? Your error is coming from here. So you have the original model, which is y equal to, for example, xb or bx plus e. And then your estimation is y equal to xb, something like this. So based on these two, and then you can compute error or residual, which is equal to y minus y, this one. Okay, so this one has to fulfill all these requirements. The first one is the error or residual has to be normally distributed. And the second one is the variance has to be homogeneous, not heteroscedastic. And then it has to be homoscedasticity, fulfill the homoscedasticity. And the third one is you have to free from multicollinearity. If it is only one independent variable, you don't have to check this one. But if you have more than one x, so you have to check this multicollinearity. Why? Because if more than one, and then you will have y, x1, x2, x3, and then x4, and so on, maybe until xp. Okay? So because of in here there are a lot of x, so it is possible that there is a collinearity between this one. Because there are a lot of variables in here, so the collinearity may be the correlation between x1 and x2, x1 and x3, and so on. So that's why we call it as multi-collinearity. Clear? Okay. Now the autocorrelation. Autocorrelation, it has to be free. The error has to be free from autocorrelation. So what is the autocorrelation? The autocorrelation means the error between the first observation. They have relationship with the second, the third, and so on and so on. So that's why in here it has to be free. But if your data is coming from times to time, like time series, and then you have to check it carefully. Yeah, otherwise maybe your model may be not good enough to estimate something, okay, to predict something. Because if it is there is a autocorrelation, maybe the previous observation, it will affect directly, for example, the current observation. or if there is two, like maybe the first year will affect the third year. But if it is directly, the first year will affect the second year. So that's why we have to be careful with this kind of correlation. Okay, so let me erase this one. If we don't have time for our session or for Python session, and then I can send the link or the file about how to do this in R and also in Python. And then maybe another time, if we meet again, you can ask me. Or maybe different from this schedule, because the schedule has to be done accordingly. So if you have some question which is not in this schedule, so you can ask me later.